Okay, so we're continuing with 15D with our discussion of models, and in this video we'll actually specify what models are, and then we'll talk about them more in the next video. So, as I was saying, a model for a sentence is just like a truth table row for a sentence. The model specifies just enough facts to fix the sentence's truth value, either true or false. So that's what it does. That's its job. So what does it have to do? What information does it have to contain? Well, consider whether or not, ask yourself the question, is for all x fx or some x fx true in some situation? What do you need to know? What are the facts about the situation that are relevant? Well, it depends on which things there are and which of them f is true of, and that's all. So a model for either sentence has two corresponding parts. It has a domain or a universe. That's a list of the things that there are, or the things that we're talking about, and it's, as we'll see, going to be a very short list. And two, an extension for f, which is what? It's a list of the things in the domain which f is true of. So a domain, which things are there? An extension, which things is f true of? And we suppose that each predicate is either true or false of each object. So once you've said which things it's true of, then it's false of everything else. So let's look at some examples. Okay, so in our first model, we're going to have our domain is going to be 0 and 1. So there are two things, the number 0 and the number 1. And that's it. That's all we're talking about. The extension of f is going to be 0 and 1. So f is true of 0 and f is true of 1. So is there a thing, is some x fx true? Yes, it is. Why? Well, because there's a thing in the domain 0 that's also an extension of f, of which f is true. So there is a thing that's f. And that's also the case for 1. So some x fx is quite true. What about for all x fx? Is everything true? Well, there are two objects in the domain, 0 and 1. 0 is in the extension of f. 1 is in the extension of f. And there's nothing else. So yes, for all x fx is true. How about some x not fx? Is there something that's not f? No. There are two things in the domain. There's 0 and 1. 0 is in the extension of f, so it's not the case that it's not f or unf. And 1 is in the other thing in the domain. 1 is not in the extension of f, so it's not an unf either. So some x not fx is false. Now, if the domain were bigger, if we were talking about more things, and there certainly are lots more things, but in this model we're not talking about them. But if there were more things in the domain, and some of them were not in the extension of f, then some x not fx would be true. But in this case, everything in the domain is also in the extension of f, so some x not fx is false. Let's look at a second example. Here we'll have a domain be 0, 1, and 2, and the extension of f will be the same, 0 and 1. So we've expanded our domain by adding to it one object, the number 2. So we have three objects, 0, 1, and 2. Just to be clear, 0 here is a number, and just like, so there's the number 1 and the number 2, there's also the thing, the number 0. So we're thinking of the number 0 as just one more object. Now if I say there are 0 frogs, then there are no frogs, right? But the number of frogs is 0. The thing. So that's the way in which we're proceeding. It might sound a little funny. I'm happy to talk to you about that in office hours or by email, but we're thinking of the number 0 as a thing, just like the number 1. It says the number 0 is as much of a thing as the number 1 is and the number 2 is, and so on. Okay, so some x fx. Yes, this is true because there's a thing in the domain, say 1, that's also an extension of f, and 0 is the same. So there are lots of things that are f. How about for all x fx? Is this true? Well, is everything that's in the domain also in the extension of f? No, because 2 is in the domain, but it's not in the extension of f, and so it's not the case that everything is f, so this is false. Again, how about some x not fx? Well, is there a thing that is in the domain but not in the extension of f? Yes, 2. So 2 is an unf, and so there is something that's not f, and so this is true. Let's finally look at model 3, at our last example. So we'll have 0 and 1, and the extension of f will be empty. Sorry about that. There's a cat outside that's making noise. I don't know if you can hear it, but I'm going to proceed with my model. So, is something f? Well, is there a thing that's in the domain that's also in the extension of f? No. 0 is in the domain but not in the extension of f. 1 is in the domain but not in the extension of f. And nothing else is in the domain. So sum x fx is false. Nothing is f. And for the same reason, all x fx is false. Sum x not fx, well, is there a thing in the domain for which not fx is true? In other words, is there a thing in the domain for which f is false? Yes, 0 and also 1. So sum x not fx is true. So it doesn't, if we think back and we asked, is for all x fx true or not? Is sum x fx true or not? In general, what matters? Which things are there and which of them are f? But it doesn't actually matter which things there are. It just matters whether or not they're f or not. So it only matters, in other words, it matters how many there are, and of those, which one is f true of. But it doesn't actually matter that it's Alfred or Bob in the domain. It just matters whether or not f is true of each of them. So we're not going to actually worry about which ones there are, and so we'll just use numbers for convenience. And that's the way, as you'll see, it's going to work in the invalidity module, which is where in the program you work with models. So we're not quite done with talking about what. So far, we've talked about if you need to specify a domain, and you need to say what the extensions of the predicates are. And the domain is a list of objects. It's the thing you're talking about. The extension of a predicate is the thing that the predicates are true of. What about names and sentence letters? Well, what is the job of a name? To point at or refer to an object. So if we have a model and for a sentence and there's a name in the sentence, then the model has to give a referent for each of those names. And the referent is an object from the domain, just some object. It's the object that name is being used to talk about. And so the sentence fa, that's going to be true in a model if and only if the referent of a is in the extension of the predicate. Sentence letters, just give them a truth value, just like truth table row does. So sentence letters are easy, and they usually won't, or they're simple to interpret. They usually won't show up in our models. We won't need them because when we're doing models for sentences, our sentences will not have sentence letters in them. But if a sentence letter happens, if you're doing a model for a sentence that happens to have a sentence letter, just give the sentence letter a truth value. That's all you need to do. And the truth values, so that tells us, now we know how truth values for atomic sentences are fixed. It's right here. The sentence is true if in a given model, if and only if whatever the name refers to is in the extension of the predicate letter, and a sentence letter is true if the model says it's true, and a truth functional connective sentence has its truth value determined in the way, according to the truth tables that we've looked at already, so that they're determined in the same way. So a conjunction is true if and only if both of its components are true, and so on. So a model then has to have a domain. It has to be a non-empty domain, so there's always at least one object in the domain. It has extensions for each predicate in the formula or formulas. It has a reference for each name, if there are any in the formulas. And it has truth values for each sentence letter in the sentences or formulas, if there are any sentence letters. And the general notion of an extension, so we can say that we talked about predicates having extensions, but we also talk about names and truth values having, names and sentence letters having extensions, and that's just whatever they contribute to determining the truth value of sentences in which they occur. So the name has a referent, and we say that some object, and we call that thing the extension of the name because that's what the name contributes to determining the truth value of sentences and formulas in which the name figures. Okay, so we've talked about the truth conditions of atomic sentences and of and sentence letters, and that we use the truth tables when they're relevant. What about formulas with free variables? I haven't talked about those yet. So fx is true. Well, okay, so if I say that's tall, you think, well, which thing is tall? If I have a thing in mind, then that's tall is true if and only if the thing that I have in mind is tall. If I don't have anything in mind, then that's tall isn't true or false, because the word that isn't referring to anything. Free variables work the same way. By itself, a free variable doesn't refer to anything. By itself, a sentence with a free variable is neither true nor false, because the sentence, to have a truth value, needs for the free variable to refer to something. Okay. But we can assign objects to free variables, so we can say that fx is true when O is assigned to x, if and only if O is in the extension of x. So we can say, that is tall is true when this thing is assigned to that, if and only if this thing has the property of being tall, which it doesn't. And so, yeah, it works. The free variables and pronouns work the same way in that respect, that by itself doesn't refer to anything when it, unlike a name. When it doesn't refer to anything, sentences in which it occurs don't have truth values, but you can assign objects to the free variables and pronouns, and then when you do assign an object, then the sentence gets a truth value. So what about fx then, if fx then gx? Well, so assign O to x again, and that will fix the truth values of fx and gx when O is assigned to x. Either O is or is not an extension of f, either O is or is not an extension of g. And then the truth value of the conditional is determined by the truth values of fx and gx when x is assigned to O. So, if f is false of O, then fx is false, and so the antecedent of the conditional is false, and so the conditional is true. If g is true of O, then gx is true when x refers to O, and so the consequent of the conditional is true when x refers to O, and so the whole conditional is true when x refers to O. So that's how free variables work. So in the next lecture, I'll talk about how how quantified sentences, existential generalizations, universal generalizations get truth values, and then talk about a few other issues with models. And then in the last video, we'll do some more examples. And then you'll have some homework to do with models as well.